All right. So we're very happy to have Misha Usatyuk visiting from KITP, and he'll tell us about near-extremal black holes. Thank you.
Great, thank you so much. So today I'll be telling you about near-extremal black hole evaporation. And this talk is based on 3 papers, 2 of which are out and 1 of which is a work in progress. So here's a broad outline of the talk. I'm going to first begin by telling you about classical and semi-classical properties about near-extremal black holes. Then I'm going to tell you how we're going to try to understand the quantum physics of these black holes, which is through the gravitational path integral. Then I'm going to explain how fluctuations in the metric give you quantum corrections to various properties of near-extremal black holes. And the point of the talk is to explain how these large quantum corrections modify how the black holes dynamically evolve in time, namely how they evaporate by emitting neutral particles such as photons and gravitons, and also charged particles such as electrons or positrons. And so the evaporation portion of the talk will be split into 2 sections. And then finally, I'm going to tell you how to combine both the neutral and charged particle emission to tell the story of how a near-extremal charged black hole in our universe would evaporate. So let's get started with semi-classical black holes. So this talk is all about near-extremal black holes. So what is a near-extremal black hole? So in general relativity, black holes are parameterized by 3 parameters: a mass, an electric charge, and an angular momentum, J. Now, we can consider fixing the charge Q and the angular momentum J and asking for what values of the mass does a solution exist in general relativity. And a solution exists so long as this inequality between the mass and the charges is satisfied. This inequality is a little non-trivial because the mass appears both on the left and the right-hand side. It can be exactly solved if you want it to solved. So a black hole that saturates this inequality, making it an equality, is known as extremal, whereas a black hole that nearly saturates it is called near-extremal. And in this talk, we're going to be talking about black holes that nearly saturate this inequality. So what makes near-extremal black holes special compared to all other kinds of black hole solutions? They're special for 2 distinct reasons. One is they become very cold near extremality. In fact, at extremality, when this equality is saturated, their temperature is exactly 0. So they'd be colder than all other objects in the universe, and they wouldn't emit any Hawking radiation. The other feature that makes them special is they develop long ADS2 throats, which I'll show on the next slide. And a lot of the developments of the last few years have come from understanding the dynamics of these long ADS2 throats. So in this talk, we won't consider a black hole with a general angular momentum J and a general charge Q. We're going to restrict to charged black holes just carrying some electric charge big Q. So we're setting J to 0 in 4-dimensional asymptotically flat space. But black holes with angular momentum are going to come back and appear a little bit later in the talk. But if you'd like to know the story, what happened with general Q and J, you can ask me afterwards. The story is quite rich and depends on, if you're an ADS or DS. But here we're just going to consider the simplest case in flat space. Okay, so we're going to consider charged black holes, and the inequality becomes the simple relation that the mass of the black hole has to be greater than or equal to the charge. And I've written the temperature close to extremality here. I've discarded a denominator. Clearly, it goes to 0 at extremality. The solution is given by a metric written here and a gauge field. Okay. On the right, I've drawn a space-time diagram of what a charged near-extremal black hole looks like. So this x-axis is the radial direction in these coordinates. And we start at the outer horizon of the black hole. That's where you solve f of r being equal to 0. Well, it has 2 solutions, but you take the outermost one. And then the radius increases to the right. And I've also drawn a circle direction. This circle direction represents the size of the 2 spheres. So if you look at this metric, there's a dt squared component, some dr squared component, and then there's a 2-sphere tensored on. So close to extremality, if we zoom in to the near horizon region, the metric ends up looking like an ADS2 factor coming from the dt squared and the dr squared, although it's not obvious in the way I've written it, times an S2 where the S2 has approximately constant size. And then very far from the black hole, it just looks like asymptotically flat space, and the size of the sphere grows again. The size of the ADS2 region grows as temperature goes to 0. I've written it here, and it becomes infinitely big at 0 temperature. I should make one comment, which is that all of the black holes we're going to discuss in this talk are very unrealistic. So astrophysical black holes are in a completely different parameter regime. A common estimate people make for how much charge to mass a typical astrophysical black hole carries is you consider putting, say, an electron outside of a black hole, and you ask what charges and masses should the black hole have so that the gravitational attraction on the electron cancels out the electrostatic repulsion. So you set the electric force equal to the gravitational force, and you get an estimate that charge to mass is 10 to the minus 22. And here we're considering cases where charge to mass is approximately 1. So highly unrealistic. Just a comment. Okay, so once we have such a black hole, we can ask what's the standard story of how it Hawking radiates? Well, it has a temperature, so it's going to emit all kinds of massless particles, photons, gravitons. The production of massive particles would be exponentially suppressed. So what happens? Well, on the left-hand side here, I've drawn this squiggly little line. It's a mode. It's a wave of some frequency. It's generated at the horizon, and it tries to propagate down this long throat and escape to infinity. I haven't drawn it here, but the black hole geometry creates an effective potential barrier for this mode to tunnel through. So just because a mode is generated at the horizon due to Hawking's effect doesn't mean it will penetrate through the barrier and make it out to infinity. Many modes are reflected back into the hole. On the right, I've given the semi-classical flux predicted from Hawking radiation. So the black hole has some inverse temperature beta, and in this formula, we have this thermal factor in the denominator. The integral over d omega times omega is because you want to count modes of each frequency omega and then multiply by their energy, which is omega. And the numerator, you have this r plus omega squared piece. This is the probability that a mode with frequency omega can tunnel through the potential barrier and escape to infinity. This is known as a gray body factor. And here I've taken a low energy approximation where this gray body factor can be solved analytically. But the gray body factor asymptotes to 1 because the probability of a very high energy wave to tunnel through a barrier is 1. But the end result is the flux coming from Hawking radiation for, say, a massless scalar in the S-wave figure looks like this plot, and it's peaked at a frequency given by the temperature of the black hole. Very standard story. Okay, but if the black hole carries electric charge, it can also produce charged particles. How does it do that? Well, we know from Schwinger that a background electric field will pair-produce electron-positron pairs, say, in empty flat space. Schwinger's decay rate is given here on the screen, and this is the decay rate in just, Minkowski space without any black hole, et cetera, et cetera. But based on this formula, we would expect a black hole, which has an electric field outside with this magnitude, should pair-produce electron-positron pairs. So the electron might be the blue little particle, and the positron might be the red particle. They're created out of nothing, and then the blue particle might fall into the black hole, while the positron would be accelerated by the electric field out to infinity. Once this process concludes, the black hole loses a little bit of charge. It loses the charge carried by the positron, so the final charge is big Q minus little q. And it also loses some mass. It loses the energy of the red particle. So its final energy is m minus the energy of the particle, which has to be worked out from the dynamics of this particle getting accelerated. So it's maybe not immediately obvious, but this process drives the black hole further from extremality. So whereas Hawking radiation gets you closer to the extremality bound, charged particle production will dynamically get you further from the extremality bound. Now, let me make some additional comments. So this is maybe unintuitive, but the electric field for black holes actually decreases the more charge the black hole carries. That's because the radius of the outer horizon, R plus, also scales with big Q. So when you calculate the electric field, right, it's big Q over the radius squared. That ends up being big Q divided by big Q squared. So the electric field goes as 1 over big Q. So the more charge a black hole has, the weaker the electric field is outside the horizon. One other comment is that pairs want to be produced where the electric field is strongest. And because the electric field falls off with radius squared, pairs want to be produced in the near horizon region, so as close to the horizon as possible. So we can just do a naive approximation to actually calculate the pair production rate. We can take Schwinger's formula and we can integrate it over the black hole spacetime and ask if we're sitting far away from the black hole with some standard time coordinate t, and we count how many positrons the black hole emits, what do we expect per unit time t? So integrating over the whole black hole spacetime, we got this answer. And this rate splits up into two different regimes. So this rate is controlled by this exponential factor, and then it's got some prefactor that's maybe not as important. The exponential factor is the mass squared of the charged particles, say the lightest charged particles in your theory, divided by the charge of those particles, multiplied by big Q. Now, there's one fact, which is that the mass of the electron divided by the charge of the electron is like 10 to the minus 21 or 22. So the factor in the exponent is very small, and it needs to be compensated by a very large factor of big Q to be exponentially suppressed. So what kind of black hole do you need? How big does the black hole have to be until the production rate of charged particles is very small? Well, the black hole has to be greater than 10 to the 5 solar masses. At that point, this exponent becomes a large number and suppresses the production rate. In terms of the number of electrons you need to form the black hole from, it's approximately 10 to the 44 electrons. What does this say? It tells us that if we have an extremely big black hole with a mass greater than 10 to the 5 solar masses, which is near extremal, it will only very rarely produce charged particles. But a black hole much smaller than that, say if we formed one from quick collapse, it would start producing just a ridiculous number of charged particles and would very quickly discharge. This is what this calculation tells us. So this is the standard, maybe semi-classical story for how charged black holes evaporate. Okay, let's discuss quantum black holes now. So a basic assumption in quantum gravity is that black holes are quantum systems no different than heavy atoms. Of course, we don't have a theory that reproduces this, a bulk theory that reproduces this. But we can use atomic physics as a benchmark of what we want our quantum theory to reproduce, right? We want discrete energy levels for our black hole. We consequently want discrete emission lines. We'd like to get selection rules. So we'd like transitions between states to satisfy standard selection rules in quantum mechanics. One other thing that happens in atoms is that we get loop corrections to energy levels of the hydrogen atom, as an example, from the lamp shift. That's another thing we might want for black holes. So we'd like a bulk theory that reproduces the above. And the surprise is that for near-extremal charged black holes, the gravitational path integral is a bulk gravity theory that can reproduce some of the above features. And this has been appreciated over the last few years. And we're going to see large quantum corrections in a moment. Okay, so the framework we're going to use to analyze these black holes is the gravitational path integral. What are the rules of the gravitational path integral? Well, we specify an action, say the Einstein-Hilbert action coupled to Maxwell and maybe matter, maybe the matter of the standard model. And then we set some boundary conditions at infinity. And we sum over all Euclidean geometries that satisfy our boundary conditions. Here, I'm going to abuse the figure I've been using throughout and maybe change notation a little bit. Now I'm going to take this circle to represent the size of the thermal circle. So the boundary conditions I'm going to set for my path integral is that the time direction is periodic with periodicity beta, and I might set some chemical potentials for my gauge. I'll set boundary conditions for my gauge field that might involve fixing some chemical potentials or something of this sort. Or I might set boundary conditions for the gauge field such that the charge at infinity is fixed to be big Q. Now, when I do this path integral over Euclidean geometries, I want to interpret it as a thermal trace over some quantum gravity Hilbert space. So I'm calculating the object on the right-hand side, and this equality is really some kind of assumption or interpretation of what I'm calculating. So what happens if we do this calculation at saddle point level? Well, at saddle point level, we want to find a Euclidean geometry that satisfies our boundary conditions. And how do we get that? We just take our Lorentzian black hole. We analytically continue the time to be imaginary to get a Euclidean metric. And now we periodically identify the time with periodicity beta and make sure the black hole is smooth so the solution is on shell. If we do this calculation, which Gibbons and Hawking did in '77, we get this answer on the second line, right? So just evaluating the classical action, we get e to the minus beta m plus a term that we can interpret as an entropy of the black hole. That's a saddle point value. So this answer seems to be consistent with some kind of quantum mechanical interpretation. Okay, but we want to do a little better. We want to calculate fluctuations around the saddle point. So what we want to do is we want to split our metric into the classical metric we just used, plus some fluctuating mode, delta Gn, and we have some sum over fluctuations. And An is some real number that we integrate over in the path integral to integrate over metric fluctuations. And we do the same thing for the gauge field. Now, this was actually studied in the early 2010s by Ashok Sen and many authors. And when they did these fluctuations, they did them at one loop level. And they found that this calculation just gave a modification to the entropy. It gave a modification to S black hole of M that was logarithmic in the area. And this was analyzed by many authors in many different theories in many different settings. But a certain set of modes were missed in these calculations, which are now known as Schwarzian modes. So what happens when we include these Schwarzian modes? What these Schwarzian modes do is they give you very large corrections when the temperature of the black hole is very small. There's an emergent energy scale for each black hole with charge big Q. The emergent energy scale is the Planck mass divided by big Q to the third power. If you work out the action for these Schwarzian modes that were missed before to say quadratic order, don't worry about the n squared factors. The epsilon n is a real number you integrate over. You find their action is the temperature of the black hole divided by this energy scale. So these modes become very light when the temperature is close to this breakdown scale, and they become very important. If you work out what these corrections do to the number of quantum states of the black hole, you get a curve that looks like the following. So here I relabeled the mass of the black hole to be the energy. When the energy is 0 all the way on the left, that corresponds to m being equal to q. So that corresponds to an extremal black hole. And as we move on the right, we get away from extremality. The dotted line, I don't know if you can see it, is the semi-classical answer. So it's just the classical value of the horizon area of the black hole divided by 4 g Newton. And the solid pink line is the answer for the number of states when you include these modes at one loop level. Some intuition for these modes is that they're fluctuations that are very close to the horizon, to the Euclidean horizon of the black hole. So this is pictorially what this blue circle is. Good. So they give a very large modification to the black hole energy at this scale, or to the black hole entropy at this scale. So naively, you should expect, because we found large quantum corrections to the entropy, all dynamical processes should also be heavily modified when we reach this scale. So now I'm going to explain how these corrections modify dynamical processes. Okay, I'll first discuss neutral radiation, where we do find large modifications to the emission of neutral particles like photons and gravitons. And then I'll discuss charged particle radiation, where the surprising thing is that there are no modifications. At the time we wrote this paper, we were confused why there were no modifications. But now we understand why the modifications are small in the case of charged radiation, which I'll explain later. So let's get started with neutral radiation. So how do people deal with these Schwarzian modes? Well, they throw away the flat space asymptotics and they analyze the theory in the ADS2 cross S2 region. What you can do is you can quantize the theory in the ADS2 cross S2 region, and you get states labeled by an energy and a spin. On the right, I plotted the spectrum of the theory when you quantize it in this region. When you move vertically up, you're moving vertically up in energy, and the x-axis is the angular momentum. So we get a continuum of states for any energy that's shaded in gray. So I should mention energy being equal to 0 corresponds to an extremal black hole without any angular momentum. Now, note here that the states only exist with half-integer quantized angular momentum. So the Schwarzian theory knows that black holes have quantized angular momentum. I've given the actual density of states from the Schwarzian theory here at the bottom. It's some sinh square root E with some energy shift. Good. It's hard to represent here, but the number of states exponentially grows as you move vertically up, and it decays to 0 as you reach one of these lower bars with a dark line. One other thing to notice here is that when we increase the angular momentum of the black hole, the minimum energy for a state to exist increases a little bit. It increases by this factor of j times j plus 1 over 2 times this breakdown scale. If you remember from the first slide, black holes with angular momentum had a different extremality bound than black holes without angular momentum. This shift is exactly that, but it's a quantum version of that. So the only difference is that classically, the shift has some angular momentum squared. Here, j squared is replaced by j times j plus 1, as often occurs in quantum mechanics. Okay. So we'll see later that because the theory knows that angular momentum is quantized, that angular momentum selection rules emerge for transitions between these states, which is maybe not too surprising.
So the black hole angular momentum is quantized?
Yes, yes.
I thought you were just doing fluctuations around the background. So this is Schwarzian theories.
Yes. So the Schwarzian theory, okay, you're doing fluctuations at, okay. You're studying a background asymptotically where you're taking the charge Q to be very large. and you're studying fluctuations around that background. So when you study fluctuations, the theory knows that the black hole can have a small amount of angular momentum. When I say 0, I mean 0 times h bar. And when I say 1/2, I mean 1/2 times h bar. This is a very quantum amount of angular momentum. And this really only works because we're doing the expansion at very large Q. At very large charge Q. Yes.
Very naive question. These energy levels have anything to do with the
No.
Those also sensitive to like the horizon.
And
They're also like with some energy levels in some sense.
yeah. So quasi-normal modes are the frequencies at which a black hole rings down. And these are the actual, eigenstates of the black hole. So it would be like if I plotted the eigenstates of the hydrogen atom, right? They'd be discrete. That's what I'm plotting here. Any other questions?
You mentioned supersymmetric case at some point. Is there any difference?
There is a difference. I'll show you a plot very similar to this in a little bit. Okay, so what is Hawking radiation for a black hole? Well, Hawking radiation is just the process that a black hole is in some excited state, right? And it can decay to a lower state. And it can decay to a lower state by emitting some radiation. So how do we study how the hydrogen atom decays? Well, we write down the standard Hamiltonian for the hydrogen atom, and then we couple it to QED. That gives us some kind of interaction Hamiltonian. And we can study how one state of the hydrogen atom transitions to another state, right? By calculating a matrix element between the initial state of the hydrogen atom and the final state of the hydrogen atom with a photon. So that's what this first line is. Good. And that would tell us the transition rate from Fermi's golden rule from some initial state I to some final state L. Now, if all we know is that we're in some initial state and we don't really care what we transition into, we would integrate over all possible final states. So this would tell us the decay rate, gamma I to anything, from some initial state I to any final state L. Now, we've quantized the Schwarzian theory by throwing away the flat space asymptotics. So this theory doesn't actually know that we're coupled to flat space. And so there is no way to have these kinds of transitions just in the Schwarzian theory. We have to recouple the Schwarzian theory back to flat space. Here I have some long explanation about how to work out the interaction Hamiltonian that I add to the Schwarzian theory to recouple the near horizon region to the flat space region. It's not extremely important, but the point is the final result is the interaction Hamiltonian corresponds to, the interaction Hamiltonian is given by an operator curly O, which I've drawn here. And this is an operator in the ADS2 Schwarzian theory. It's like a boundary operator in ADS CFT. It's like a CFT operator in ADS CFT. And these creation and annihilation operators, A and A dagger, are mode functions at asymptotic infinity that say create a scalar field with angular momentum 0 with frequency omega. And there are similar interaction Hamiltonians, say for the photon and the graviton, where you would create different angular momentum modes of each of those. And yes, I don't think I'll display any of these interaction operators.
Should I think of these expressions as Einstein? So you have like any shoots.
Yes. So the Schwarzian theory gets us the spectrum of the black hole, and then we can analyze how we can then couple the theory to flat space and analyze how, as we time evolve, the states evolve.
Can you say a little more why you don't need to worry about quasi-normal modes, as Julia was saying? Like why you're only interested in these, like, so you're kind of building a UV model of the black hole right now.
Yes. if I perturb the black hole with a scalar field, it's true the scalar field will ring down, right? And it will ring down with some characteristic frequencies omega n. I'm just.
So your initial state, you're not shooting, like you're not shooting a wave in to probe the black hole. The background.
That's right. The initial state is just a black hole at some energy, but you could perturb it and study that. But that's just a different question than what I'm analyzing here.
And if you turn the charge off, without and then this,
Turn the charge off.
like if you just charge of black hole, then this energy level will change.
Yes, this whole picture would change. I mean, the starting point here was we consider a black hole with a charge Q, big Q, right? And we did some asymptotic expansion in big Q. So it doesn't, yeah.
So it was important that all goes wrong.
Yes, 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 yes. Any other questions? Okay, let's start with something easy. Let's start with a massless scalar field. On the left and right, I've given two plots for what the energy flux looks like for black holes at some initial energy EI above extremality. So on the left, the black hole is 100 units of E breakdown above extremality. And on the right, the black hole is 1/10 of a unit E breakdown above extremality. In the blue curve, I have the answer from Hawking, just a naive thing you would do. And the orange curve is the full quantum mechanical answer, right? And it's simple enough that I can write it on this slide. Here it is. So you see when the black hole is sufficiently far above extremality, the full quantum answer approaches the semi-classical answer. And the QFT in a curved spacetime is a good approximation to how the black hole behaves. However, very close to the edge of the spectrum, we see the two answers differ drastically. We don't even see where the semi-classical answer peaks. So obviously, if the black hole is only 0.1 above extremality, it can't emit more energy than that into radiation, right? Otherwise, you would violate the classical extremality bound, and naively, you would form a naked singularity. So this is one of the issues with the semi-classical answer that was pointed out in this paper by Preskel, Schwartz, Shapir, Trivedi, and Wilczek. The full quantum answer, taking into account the Schwartzian corrections, knows where the edge of the spectrum of the black hole is and accounts for that.
So you did a one-loop computation, right? You got this exactly.
Say that again.
You did a one-loop computation.
That's right.
You got the result exactly for when this breakdown happens.
For when this breakdown
for
happens.
EI, like the quantum curve ends exactly at EI.
Oh, that's right. That's right.
Why isn't some perturbative calculation that should only approach the answer? Like the fact that the one loop computation is so large, how can I trust the loop expansion at all?
Yeah. Good. Okay, good. Let's distinguish two things. When we were doing this calculation, we were taking the Einstein-Hilbert action, right? And we were expanding it in fluctuations of the metric to arbitrary order. I showed you the answer to second order in the expansion. The expansion has the following structure. When you consider field fluctuations, let's write an effective action. We're going to get a term that goes as temperature over E breakdown times, let's say, field fluctuations squared, field fluctuations to the third, field fluctuations to the fourth, ... This gives you some nonlinear theory. This theory turns out to be one loop exact. So the answer I showed was for this reason. So it was one loop exact to all orders in these perturbations. There's another set of perturbations that appear at T squared, E breakdown squared, and I guess you would also have maybe delta G to the third, maybe squared, terms like this. Terms like this have not been included in the calculation. But what you can do is you can try to analyze them perturbatively, taking this theory as the defining theory, right? You can bring this down, and you can ask, how does this modify the density of states that I computed? And what you'll find is that you can argue that very close to the edge of the spectrum, nothing happens, because what controls how the curve behaves close to the left edge of the spectrum is the smallest power of temperature. So when we calculate the Euclidean partition function as a power of temperature, all of these terms give you something that's t to the 3/2 power, then something I classical over E breakdown to the 3/2. And there are some arguments that things like this give you higher powers of t. When you do the inverse Laplace transform to find the spectrum, things like this do not modify behavior close to the edge, but will give you some modification in the middle. The fact that there's a sharp cutoff in these plots at EI really comes from knowing the number of states close to the edge. It doesn't care about anything in the middle. So these higher loop effects might potentially modify this plot somewhere here, somewhere in between, but it's not going to shift to the EI behavior.
I'm still confused about like Euclidean versus Lorentzian, because like the path integral you computed in Euclidean and then you find the Schwarzschild. And you just sort of analytically continue that back to Lorentzian to set up this
So
issue for this.
with the Euclidean theory, right, you can calculate a density of states, and you can calculate the number of states of any energy. And in a Euclidean theory, you can also calculate correlation functions. So you can calculate objects like this. EI, and you have some operator of some scaling dimension, delta, EF. I can calculate objects like this in the Euclidean theory. Once I have all this data, I can do any calculation I want in Lorentzian signature. All right, I don't know if it's visible with the podium. Okay, any more questions before I move on? Okay, great. So in our universe, we don't have a massless scalar, so Hawking radiation will be dominated by photons and gravitons. This is what the plot looks like for photon emission. On the left, we have a black hole, which is very far above extremality, and I've given it a large amount of initial angular momentum. It has J equals 40 units of angular momentum. And now when it emits a photon, let's say the photon only carries angular momentum 1, it can transition into 3 possible final states, right? It can go to a state with 39 units of angular momentum, 40 units of angular momentum, or 41 units of angular momentum. All of these transition rates can be calculated, and their plots are given here. So the quantum answer is again in orange, and the semi-classical answer is in blue. In this plot, these lighter shaded plots add up to their corresponding full shaded plot. Okay. And on the right, I've given a black hole in a very quantum regime where it just has 2 units of spin and it's at 6 E breakdown. And you see the full quantum answer is just completely radically different from the semi-classical expectation. One other fun fact. So I told you this time scale earlier for electron production to be exponentially suppressed. Sorry, I told you the mass scale at which electron production is exponentially suppressed. You can ask how long it would take a black hole to emit 1 photon if it was near extremal at the breakdown scale with 10 to the 5 solar masses. Takes 10 to the 760 years. So it takes a really long time to emit even a single node. But one other fun comment is that because basically all dynamical properties of the black hole are modified, it was pointed out in these papers that if we had such a black hole, we could just scatter a wave off it and measure some absorption cross-section and see that it is behaving in a very quantum way and order one time, just by scattering a wave off it. So that's a way to probe these black holes very quickly. Good. There's one other interesting thing with neutral radiation, and that is that angular momentum selection rules forbid certain transitions that are allowed at second order in perturbation theory. An example from atomic physics is the 2s to 1s transition in the hydrogen atom. This transition takes about 1/10 of a second, which is quite long by atomic physics standards. That's like a pretty stable state. The way this transition happens is that you can emit two photons that are entangled. Their spins are entangled so that they come out in some singlet state and don't carry any angular momentum. So when the black hole is cold enough, the only quantum states, when it can no longer populate states of spin half, the only quantum states have spin 0. So if we have such a black hole, we might think that we're stuck. We can't emit any photons. That's actually not true. And through these kinds of processes, we can emit 2 photons, but now, okay, I don't have, the expression for this process is a lot more complicated, right? Second order and perturbation theory processes are very complicated. But if you have all these matrix elements, you can just calculate all these rates. It takes 10 to the 450 years to emit diphotons. And the calculation exists for gravitons as well, and it's similarly slow. Okay, I promised supersymmetric black holes. So you don't need to know anything about supersymmetry, maybe even ignore what's on the left-hand side here. But in theories of supergravity, you also have charged black holes that are classically indistinguishable from everything I've told you so far. The metric is the same, the gauge field is the same, the geometry is the same. But now when you analyze these loop effects, you find their quantum spectra are very different. So these theories have, these charged black holes at extremality are BPS particles. They're BPS states, and so they're protected. So when you calculate the number of quantum states, what you find is the following. Black holes that have spin 0 have a large ground state degeneracy. I've denoted that by this big red bar with an e to the s naught. There's exponentially many states sitting there at j = 0. Then you seem to have a gap in the spectrum. And you have a gap in the spectrum until some particular energy, where you get continuum states again. So you could ask, one other thing to say is that the extremality bound is slightly modified for supersymmetric black holes compared to non-supersymmetric black holes. Good. Now you can ask, if we start in some excited state here, how would the black hole decay down to BPS states? Okay, there's some details about adding matter to the theory, but suppose we start in this state all the way at the top with spin 0, and we just have some scalar particles. Then because of the supermultiplet structure, you can decay to many different states, and their matrix elements are all slightly different. So the full quantum answer is this orange curve, and it's a sum of many different transitions between many states and supermultiplets labeled by psi, chi, and L. Good, and you can see that the emission ends precisely when continuum states end. However, there's also a transition probability for the black hole to emit all of its energy and transition to a BPS state. That's what this red arrow is. And so if you have such a black hole and you were looking at it, you would see that you get a lot of radiation out at one particular frequency, which is kind of similar to what you see in atomic physics. Yeah, and at the bottom, I also highlighted some differences that supersymmetric black holes had compared to their non-supersymmetric cousins. Okay, let's discuss charged particle emission. So what happens if we try to do what we just did for neutral radiation for charged particles? Well, if you add a charged scalar field into the ADS2 cross S2 throat, what you find is that from the ADS-CFT dictionary, the scalar field is dual to a boundary operator with a complex scaling dimension. And this is very confusing. So I don't personally know how to perturb a CFT with an operator with a complex scaling dimension and then calculate probabilities. They seem ill-defined. This kind of effect was also noticed long ago in a paper by Gubser. And the interpretation there was that the background was unstable to pair producing many charged particles that would then maybe float around the block. So we have to do something else. We have a different formalism that we used for charged fields. Remember, we were calculating some kind of Euclidean path integral. Now we want to add, let's say, a charged scalar field to the theory, and we want to calculate the path integral, the Euclidean path integral, with this charged scalar field. So we can integrate out the field and get some log determinant, and then we can apply the world line formalism to calculate this log determinant alongside the integral over all metrics and all gauge fields. And what we want is we want to rewrite the Euclidean path integral we get on the left-hand side in terms of some object that looks like this on the right-hand side. So we want some integral over energies with a density of states suppressed by e to the minus beta times an energy where the energy has a real part e and a complex part gamma. And from this calculation, we'd be able to extract the decay rate of a state at some energy e. What happens when we do this calculation? Well, in the world line formalism, you rewrite the log determinant in terms of a path integral over paths on your manifold. When you do this on the black hole background, you end up integrating over all these little red loops, where the loop carries some charge, little q, and it has some mass, little m. And you find that there are maybe classical saddles where these little loops like to sit. These little loops essentially give you instantons on the black hole background. Now, because the little loops carry a charge and a mass, they actually back react on the black hole. So, well, they back react on the black hole because if it carries charge by the Gauss law constraint, it has to take some of the charge from the black hole. Once you take all of this into account, you find that there's one thing I should have mentioned. In the world line formalism, we also have to integrate over any number of these little loops. So on this figure here, I've drawn a disk with 5 little loops, but we have to do a resummation where we have any number of these instantons on the black hole background. The final result, when you include the back reaction of these little loops, is that there are new modes coming from quadratic fluctuations of the metric. They correspond to where the instanton is located. So the instanton wants to be symmetrically located around the center of the black hole, and now if you move it away, it gets some light action. And this is how the Schwarzian couples to the location of the instanton.
What's the size of the little loop?
Yeah, the charge to mass ratio that you put in. So that's the classical size of the little loop. Okay, so here I've given an expression for this imaginary part of the energy. If you looked at the previous slide and just rearranged things, this is what gamma of beta should be. So we're taking the logarithm of the sum of the partition function, where we have any number of instantons k going from 0 to infinity. And we have to divide that by the pulse vacuum to extract the decay rate. There's some approximation where if the instanton action of a little loop is small, this full thing is approximated by just a single instanton. So in the case that we just have a little loop, we're doing the following integral. The blue, okay, So the integral over the red loop gives us the red factor in this answer, and the integral over all metric fluctuations gives us the blue answer in this equation. What you find when you do the calculation and put all the pieces together is a final result identical to Schwinger. So you get exactly the same decay rate that Schwinger found. And we had a much more elaborate calculation in the paper where we did the path integral over any number of instantons and we resummed things in tricky ways. And you get corrections to this answer that are subleading, but this is still the leading final answer. So very surprisingly, charged particle production is completely unchanged. Let me tell you why it's actually unchanged. So the reason it's unchanged is that, remember these large quantum effects came from metric fluctuations. It turns out at very small temperature, the metric fluctuations are confined to be very close to the horizon. Sorry, I don't have a picture. Right, the important modes of the metric are confined very close to the horizon. But charged particles are produced through the Schwinger effect. And the Schwinger effect only cares about the local electric field. So if the particle is produced, I don't know, a little bit away from the horizon, it doesn't really care that there are very large fluctuations in the metric very close to the horizon. So you wouldn't expect its production rate to be modified. And because the charged particles can be produced anywhere in the throat, most likely they're not going to be produced in the region where quantum metric fluctuations are large. So this is the physical picture why charged particle production is unaffected.
I thought you said that the electric field was largest at the horizon, so the production rate was largest at the horizon, right?
It is largest at the horizon, but the electric field is roughly constant everywhere in the throat. Sorry, I should have said that as well. So if it's yeah.
But so the rate is like maximized precisely what the corrections are, right? No.
The rate is maximized exactly at the horizon, but there's just like so much space everywhere else, right? The throat is extremely wrong, so the volume just wins out. Yeah.
Do you have an intuitive picture of why you say that these large metric fluctuations are always very close to the noise?
Yes. So if you like literally just like work them out, like in the full 4D geometry, and you plot them as a function of radius, as you decrease the temperature of the black hole, the actual fluctuations in the plot are just like localized super close to R equals R plus.
I see. So that's very different from like the regime where the ES2.
No, it's exactly the same regime.
Right, but that's what I was.
Yeah.
So everywhere where there's ADS2, there's large metric. Pretty much.
Yeah, from the perspective of the full 4D geometry, even though you have a very long ADS2 throat, in the full 4D geometry, the metric fluctuations are like literally basically at the horizon, not in the rest of the throat. So they're confined very close to the Euclidean black hole horizon. Okay.
Like I just take start to some charge and then put a contribution on top.
Yes, you start with Reisner and Nordstrom, right? And then, well, people have already worked this out. You don't need to compute anything. You go to these papers, you find a metric fluctuation delta G, which is a function of the coordinates. Yeah. Yes. They're off-shell fluctuations, and you can just plot what the fluctuation looks like. And there are papers that do this. I'm running low on time, so I think I will skip the super radiance section to quickly tell you the story of a charged black hole. So here's the setup. We're going to be in 4-dimensional asymptotically flat space, and we assume that we don't have like interstellar media or any junk floating around, right? We're just going to start with a very big black hole carrying a lot of charge. And if you want, you can give it some angular momentum as well. So what happens to this big black hole over time? Well, right, and we're starting in the regime where the mass is greater than 10 to the 5 solar masses. So the first thing that happens is the black hole is going to lose its angular momentum due to photon and graviton production. So photons and gravitons are going to carry away nearly all of its spin. And charged particle production is exponentially suppressed, so all it can do is radiate photons and gravitons. We've assumed here that the initial black hole we started with is bosonic. So it has some integer amount of angular momentum. But it doesn't really matter, as you'll see in the next. Then, over a very long time, over 10 to the 760, 750 years, the black hole is going to get into a regime where the Schwarzian corrections are important, right? So it just ping-pongs down in energy levels until it gets to this very quantum regime. And it loses access to states of various amounts. Yeah, it loses access to states where the black hole has, 100, 10, 5 units of angular momentum fairly quickly. And eventually you get into a regime where the black hole has like 0 angular momentum, right? And the only way it can emit particles is through diphoton or digraviton emission. And this takes a really long time, but okay, it does that. So one interesting point is that it's going to spend the majority of its lifetime in this very quantum regime where Schwarzian corrections are important. Another interesting point is that because the Schwinger decay rate is exponentially suppressed in Q, you're going to reach exponentially close to extremality by neutral radiation emission. So the minimum mass you're going to reach is going to be big Q plus some order 1 factor times something which is exponentially small in big Q. And I should also say that quantum mechanically, there's still tons of states of the black hole. So you're not going to run into some funny issue where you have order 1 states, even if you're exponentially close to extremality. Okay, good. What happens next? Very, very rarely, you produce an electron. So what happens? Well, we have to change plots because in one of these plots, the charge of the black hole is fixed. So here I've assumed I started in some state with spin 0, and this red line is me emitting some electron and jumping to spin half. This plot isn't really to scale. Really, this red line should take you way up above in this vertical axis, but I can't represent that, okay? Emitting an electron will decrease both the mass of the black hole and the charge, but you're going to end up very far above extremality if you work out how much energy you actually lose. And now the black hole becomes fermionic. Now you're going to have transitions between states with half-integer quantized momentum. Say by emitting photons, you now end up, after waiting a long time, in a state that has spin half. And you can't reach a state of spin 0 by emitting photons or gravitons. However, even if you're in a state of spin half, you could still emit photons because 1/2 tensor 1 is 1/2 plus 3/2. So in this case, you're not kind of stuck with only diphoton emission. You can emit single photons, but you can't emit gravitons because 2 tensor half does not contain half. And then after some very long time, you're going to emit another electron and end up in a state with spin 1 or spin 0, and we're going to go back to the first slide. Okay, and this process is going to slowly repeat for a very long time until you reach the point where Schwinger pair production isn't exponentially suppressed. At this point, the electric field is strong, and you just like pair produce tons of electrons, and you get a Schwarzschild-like black hole that continues evaporating in the standard way. Interesting. Okay. So what's the conclusion? Well, near-extremal black holes behave very similar to atoms. With the Schwarzian theory, we can get angular momentum selection rules. We can see forbidden transitions. And we can't see discreteness of the spectrum, but say in the BPS context, we can see isolated states, isolated BPS states, which are separated from everything else in the spectrum. Now, there are large quantum corrections to neutral particle production from such black holes. They are scalars, photons, and gravitons. And I didn't have time to explain it in this talk, but you also get large quantum corrections to other dynamical processes involving black holes, such as absorption cross-sections and things like that. But you get small corrections to charged particle emission, which I explained the intuition for a little bit earlier. And if you kind of take all of these effects together, you can tell the full evaporation history for a large charged black hole that you would have in, say, asymptotically flat spacetimes. So thank you.
Because you like force yourself in this regime of large charge, like in large mass, so like does that guarantee that like nonlinear corrections to Einstein-Hilbert action? Do you assume minimal coupling too? Like, is it ever possible that non-minimal couplings like become relevant that they have not taken into account here?
Your question is if higher curvature corrections modify the story.
Yeah, higher curvature, higher field strength, like yeah, whatever, like other higher operators that you can add to your action. And you're always in a regime somehow, or can you force yourself into a regime where they are always not relevant for the story?
Yeah, so I guess one way to phrase the question is if I added f to some power n or some like higher curvature correction to the action, and I did the expansion for the Schwarzian modes, would I find that and I find that any term like that gives me a correction at one loop order that's more important than the Schwarzian effect. That's one way to phrase the question, I think. Well, the Schwarzian corrections don't come from fluctuations of the gauge field. So my feeling is that higher F terms are okay. I don't see an immediate argument. Yeah. It sounds like you might just have a shot.
Like I think how big the field strengths can be. Because if the field strength can be large, you can set them to their background value and then still have like some Riemann or whatever like coupled to this. And then you can get modification from large field strength through your metric fluctuations, right? Beyond normal Einstein.
Large field strength. Well, at very large Q, the field strength is small, right?
So then you can argue away, like I guess this higher F corrections.
Well,
the same, but like you could I just don't know like how big are the gravitational field strengths? Probably not so big because
the curvatures are also going to zero for very large Q.
Yeah, so then
But I have no way to argue that you don't get some linear in T term if you add some general thing to the action.
Like
adding spin to the black hole. I mean, now you're able to look around. And then expand J over N with respect to the charm. How does it isolate the other side of right?
Yes, yes. Maybe to rephrase the question, is the question if I had a Kerr-Newman black hole and I considered a near-extremal Kerr-Newman black hole, are there Schwartzian corrections? And the answer is yes. That's the simplest question. The evaporation of Kerr-Newman black holes hasn't been fully worked out yet, but my expectation is that you're going to lose all the angular momentum very quickly, just to photons and gravitons, and you're going to get into the case of a charged black hole. Yeah, charged black holes are quite special in that you don't run away from the near-extremal regime due to a dynamical process, sufficiently large mass.
What about magnetic?
Magnetic? Yeah, good. Then the good.
Like this curve out.
Kerr-Taubnut. Let me just answer the case for pure magnetic black holes. Then the limiting factor is you want the black hole to be large enough so the magnetic field is weak enough so you don't pair produce monopoles. And that also sets a bound on how big the black hole has to be depending on the mass of the monopole. And we have some estimates of that in the paper. The magnetic black hole can be very, very light, and then something similar to this story goes through and you don't produce monopoles just because they're ridiculously heavy.
All right, so no other questions. Let's thank Misha again.